Right now, as this plays, there are over 39,000 cataloged objects in Earth orbit. That's the number from ESA's 2025 Space Environment Report. About a third are payloads, active and dead satellites. A small fraction are rocket bodies, spent upper stages drifting after delivering their cargo. And the majority, over 23,000, are debris fragments, shrapnel large enough to track with radar. Below the tracking threshold, the picture gets worse. Over 1 million objects between 1 and 10 centimeters, roughly 130 million smaller than that, paint flecks, frozen coolant droplets, shards of solar panel, all of it moving at around 28,000 kilometers per hour. At that speed, a fragment the size of a marble carries the kinetic energy of a hand grenade. A bolt hits with the force of a car crash. A dead satellite colliding with an active one doesn't just destroy it, it creates a cloud of new fragments, each on its own trajectory, each capable of triggering the next collision. Here's what depends on this narrow band of orbit staying functional. GPS, meaning navigation, time-stamped financial transactions, emergency coordination, weather forecasting, the polar orbiting satellites that feed roughly 85% of data into forecast models. Then communications, Starlink, maritime, aviation, military, disaster response. And Earth observation, ice sheets, deforestation, sea level monitoring. If you've checked a weather app today, that's low Earth orbit at work. If a map guided you somewhere this morning, same thing. The infrastructure is invisible, and that's why its vulnerability gets ignored. The process by which this gets worse has a name. In 1978, NASA scientist Donald Kessler published a paper describing a scenario where the density of objects in orbit becomes high enough that collisions generate debris faster than natural decay removes it. Each collision feeds the next. Eventually, certain altitudes become unusable, not for years, but for generations. Kessler called it a collision cascade. Everyone else calls it Kessler Syndrome. The concept is deceptively simple. Objects collide. Debris scatters. Each new fragment is now a projectile on its own orbit, crossing paths with everything else at that altitude. If the fragment density is high enough, the rate of new collisions exceeds the rate at which old debris falls back into the atmosphere and burns up. The population grows on its own. No additional launch is needed. The detail most summaries leave out. This doesn't require a war in space. It doesn't need a catastrophic single event. It can begin with the steady accumulation from normal operations, spent stages, dead satellites, bolts, thermal blankets, until the density crosses a threshold. Nobody knows exactly where that threshold is. Some models suggest certain altitude bands are already at or near it. Others say decades remain. The disagreement is its own kind of problem, because while researchers argue about where the line is, the object count keeps climbing. Here's how we got here, not through accidents, through decisions. For the first 4 decades of spaceflight, the practice was simple: launch, use, leave. No requirement to deorbit, no disposal guidelines. The assumption was that space is large enough to absorb whatever gets left behind. Kessler did the math in the late 70s. The math said that assumption was wrong. The industry took another 3 decades to start listening. The first major punctuation mark, 2007. China tested an anti-satellite weapon, intercepting the Fengyun 1C weather satellite at high altitude. The impact created over 3,500 trackable fragments, with thousands more below the tracking threshold. That debris is still up there. At that altitude, atmospheric drag barely touches it. Some fragments will orbit for centuries. The ISS has performed debris avoidance maneuvers specifically because of Fengyun 1C fragments, more than a dozen times since 2007. Each maneuver burns fuel, disrupts operations, and sometimes forces the crew into their return vehicles. To be clear about what this means in practice, every operational satellite in that altitude range saw its collision risk change overnight because of one country's military decision. No legal mechanism addressed it. Nobody was compensated. Nobody was penalized. The second event, 2009, Iridium-33 and the defunct Russian Cosmos 2251 occupied the same point in space at the same moment. No weapons test, no hostile act, just a working satellite and a dead one on intersecting paths. The closing speed was about 11 kilometers per second, At that velocity, there's no collision, there's disintegration. Over 2,000 trackable fragments. The third, November 2021, Russia tested its own anti-satellite weapon, destroying one of its own defunct satellites. Over 1,500 new trackable fragments. The ISS crew sheltered in their return capsules as the debris field passed through the station's orbit repeatedly. International condemnation followed, and structurally, nothing changed. Between these three events and the steady accumulation from decades of routine operations, fuel tank ruptures, battery explosions on abandoned hardware, the slow grind of normal negligence, the orbital environment reached the state ESA describes in its 2025 report. At the most crowded altitudes, the density of active satellites is now the same order of magnitude as the density of debris. That's a sentence worth reading twice. The weapons tests get the headlines, and they deserve scrutiny, but they're not the majority of the problem. Most debris comes from decades of nobody cleaning up after themselves. The ASAT tests are punctuation marks in a longer story of institutional neglect. Dramatic, yes, but the sentence was already being written. Now, the instinct is to point at China, at Russia, and move on. But that framing misses the system. There is no authority responsible for orbital debris, no international body with enforcement power, no equivalent of air traffic control for space. The UN publishes voluntary guidelines. ESA has set a zero debris goal for 2030, but ESA governs only its own missions. The FCC has started requiring deorbit plans for new satellites, but requiring and enforcing are not the same thing. The economics make it worse. Removing one piece of debris costs tens of millions of dollars. Active removal technology exists in prototype. ESA's Clear Space 1 mission is planned for this year, the first attempt to grab a debris object with a robotic claw. Astroscale has demonstrated magnetic capture, real technology, but it addresses objects one at a time. The question isn't whether we can remove debris. The question is who writes the check. Launching is profitable. Deorbiting is a cost. Orbits are free to use. Cleanup is expensive. Every operator benefits from clean orbits. None has an individual incentive to pay. The textbook case of a commons problem, and low Earth orbit may be the most consequential commons problem of the century. Last year, HALE mentioned this problem at a dinner. Within 2 minutes, the conversation turned to, but isn't space really big? It is. The problem is that the useful part of space, the thin shell where orbits are practical for communication, observation, and navigation, is not big at all. It's crowded. And it's getting more crowded on a curve that bends upward. SpaceX alone has put over 7,000 Starlink satellites into orbit. Amazon's Project Kuiper is building a competing constellation. OneWeb, Telesat, various national systems, the number of active satellites has roughly quadrupled in 5 years. And here's the number that reframes everything else. In the first half of 2025, Starlink satellites performed over 144,000 collision avoidance maneuvers, a warning every couple of minutes, around the clock, for 6 months straight. 3 times the rate of the previous 6 months. Each maneuver is minor, a small thruster adjustment. Each one works, but the rate is compounding, and these are the satellites with propulsion. Failed satellites, dead stages, random fragments, they don't move. They're obstacles on a highway where nobody has brakes and there's no traffic control. Constellation satellites have short lifespans, roughly 5 years by design. That means continuous replacement, thousands deorbiting, thousands launching, simultaneously, in already crowded bands. A failure rate of even a few % at full scale means hundreds of uncontrolled dead satellites per constellation, each one a collision seed. There are 2 ways this plays out. Both matter because the outcome shapes infrastructure that most of modern life depends on. Scenario 1. Binding international rules. Enforced end-of-life disposal. Funded active removal, not prototypes, but operational infrastructure. Constellations maintain their deorbit commitments. The debris count stabilizes and, over decades, decreases as atmospheric drag clears the lower fragments. Orbit stays usable, expensive, regulated, functional. Scenario 2. The current trajectory. Voluntary guidelines. Underfunded removal. Constellations grow faster than regulation. A few more collisions, not catastrophic individually, but cumulative, push certain altitude bands past the cascade threshold. Those bands become debris fields. Satellites that relied on them need redesign or replacement. The economic damage runs into hundreds of billions, and certain orbits, once lost to cascade, stay lost for centuries. The data doesn't pick between these two scenarios, but it does say something that should frame every conversation about space from this point forward. ESA's 2025 report states it plainly. Even if every launch stopped today, the debris population would continue to grow from collisions among objects already in orbit. In some models, the cascade has already quietly begun in certain altitude shells, not as a dramatic event, as a statistical trend. The Venera engineers had a principle that keeps echoing the more you look at how institutions handle hard problems. Build, fail, publish, iterate. Treat the data as information, not as a headline to manage. The debris problem is generating data at an accelerating rate. Whether the system can process that data honestly, the way those engineers process theirs, is the open question. One number will decide which scenario we get, not the 39,000, not the 144,000 maneuvers. The number that matters is 0, the count of international bodies with enforcement power over orbital debris. Until that number changes, the rest is commentary. And that principle, whether a system can face its own data honestly, extends well past orbit. At the far edge of the solar system, 6 objects are behaving in a way that our models say shouldn't happen by chance. The math points to a planet. The telescopes see nothing confirmed. It's a different kind of problem, but the underlying question is the same. What do you do when the numbers say one thing and the evidence hasn't caught up?